So in this video, we'll start problem number 3 here. I don't want to complete this problem, so we won't actually be able to answer these questions A and B, mainly because this problem requires a lot of row operations, and I don't want us to sort of get lost in the weeds there. So what I have decided to do instead is we'll talk about how to set up this problem, and we'll look at the initial simplex, the initial simplex tableau for this problem. If you want to see the rest of the problem worked out, then just check out the handwritten notes that I'll be posting along with this lecture. So let's look at 3. It says that an independent local women's boutique has $8,000 available each month for advertising. Newspaper ads cost $400 each, and no more than 30 can run per month. Internet banner ads cost $20 each, and no more than 60 can run per month. And TV ads cost $2,000 each, with a max of 10 each month. And then we're also told the viewing numbers for each of those types of advertisement. So the question is, how much of each type of advertising should be used if this store wants to maximize its ad exposure? So we want to maximize the number of views given this budgetary constraint, and also constraints on the number of each type of ad that can be run each month. So maybe let's say that x1 is equal to the number of newspaper ads, and then x2 will be the number of internet ads, and then x3 will be the number of TV ads, because those are the things that we're looking for, at least for part A. And now we'll start writing down some of the relationships that we have between these variables. So again, if you'd like to make a little table like this, you can. The table is optional. You can just cut straight to the linear program if you want to. But notice that we have two things going on here aside from the general constraints about the number that you can run each month. We have budgetary constraints, and we also have these viewer numbers. So we know that each newspaper ad costs $400, each internet ad costs $20, and each TV ad costs $2,000. And that total is constrained to be at most our total budget, which is $8,000. And then we also have these viewer numbers. We know that 4,000 people will see each newspaper ad, 3,000 will see each internet banner, and 10,000 will see each TV ad. And here, this is what we're actually trying to maximize. So maybe I'll call this V for the views. So here we don't have any constraint on this. We just want this to be as big as possible. And notice that these are not our only equations or constraints that we get. We also have these limits on the number that can run each month. So we're told that the number of newspaper ads can be at most 30 each month. So if you wanted to write that as an inequality, it would look like this. x1 has to be at most 30 each month, x2 has to be at most 60 each month, and x3 has to be at most 10 each month. So those will be additional constraints in addition to this budgetary constraint that we have up here at the top. So maybe it's worth observing that x3, the number of TV ads, is constrained to be at most 10 each month. However, we couldn't even afford 10 based on our budget. If we wanted to, we can afford at most 4 TV ads per month. So it turns out that this is not going to really be relevant because our budgetary constraint already includes that we won't be able to afford more than 10 TV ads. So we don't technically need this constraint. It's possible to have redundant constraints like that. But I'll go ahead and include it in the initial simplex tableau anyway, even though it's not technically necessary, just because you can still solve the problem with it even without making that observation. But just be aware that you don't necessarily need to use all of these constraints. Or really, I should say that some of the constraints might be redundant. So it's possible that you can get away with solving the problem without them. But it's safest just to include them all. So let's write the linear program first, and then we'll write the corresponding simplex tableau. So we want to maximize V equals, so we know we'll get 4,000 views per X1, or per newspaper ad. We'll get 3,000 views for each of the X2s, and we'll get 10,000 views for each of the X3s. So our total viewer numbers would be this. And then we have some constraints. So I'll say subject to these constraints. First, we'll have the budget constraint, which says that we can spend $400 per newspaper ad, plus $20 per internet ad, plus $2,000 per TV ad, and that total, the left side here, is the total amount that we'll spend on advertising. That total has to be less than or equal to our budget, which was $8,000 per month. And then we also have the limits on each type of ad, so we know that the number of newspaper ads is at most 30, the number of internet ads has to be at most 60, and the number of TV ads has to be at most 10. So these are the 4 constraints that are going to be rows in our initial simplex tableau. We also have the implicit non-negativity constraint, which just says that x1, x2, and x3 have to be bigger than or equal to 0. We can't find negative amounts of ads. So now we'll write the initial simplex tableau here. And I'll just write this like right beneath where we're at. So for the simplex tableau, I'm going to skip the part where I rewrite these equations. So I'm going to omit the equations involving S1, S2, S3, and S4. So notice we'll need 4 slack variables because there are 4 non-trivial constraints. And then I'm also going to omit the part where we rearrange this equation to bring everything over to the left side. Instead, I'm just going to jump straight to the simplex tableau. So I'll label the columns up here at the top. We have x1, x2, x3, and then we're going to have 4 slack variables. And then I'll put the thing that we're trying to optimize over here as the label for the constant column. So this is what we have so far, and now I can start reading off the coefficients. So that first row would be 400, 20, 2,000, and then we'd have a 1, 0, 0, 0, 8,000, because we do need to include that first slack variable in that first constraints equation. And then the second one would look like a 1, 0, 0, 0, 1. We would have a 1 here in the S2 column, because our second constraint will use the second slack variable. And that's constrained to be at most 30, so that will be the 30 in the constant column. And then similarly for these others, I'll be using the third slack variable for the third constraint, and I'd be using the fourth slack variable for the fourth constraint. And then lastly, we have our objective row, so I'm going to try squeezing that in here. For the objective row, remember we move all of these terms over to the left side before we record their coefficients, and I'm also going to be suppressing the ordinary V column. So I'm not going to write the 0, 0, 0, 1 column that I would for V. So instead, I'm just going to identify V with this bottom right entry whenever we have to read off the value for V. But if you rearrange that equation, you should get a negative 4,000, and then a negative 3,000, and then a negative 10,000. And then we don't need any slack variables here, so all of those would be zeros, and the initial value for V will also be 0. So this will be our initial simplex tableau. And that's all that I wanted to do in this video. I think working through this would be more of a hassle than it's worth, but if you'd like, you can read over the handwritten notes if you want to see how this problem concludes.